If you remember back in first chapter, we talked about different ways that we can classify matter. And all matter we can either define as being something that's pure or something that's in a mixture. And if it's pure, we talked about we can have pure elements or we can have pure compounds. And when it's in a mixture, we had two different kinds of mixtures. We had heterogeneous mixtures and we had homogeneous mixtures. Well, homogeneous mixtures, that's what solutions are. And in particular, we're going to be talking about aqueous solutions. Now, most of you already know the term aqueous. I have it down here at the bottom of the slide. Aqueous solutions are simply solutions where water is the solvent. Okay? So now we need to know, well, what's the solvent? And if you're not the solvent, what are you? You're either a solvent or you're a solute. They're both components of a solution, all right? The solution is simply the homogeneous mixture of two or more substances. The solvent is simply going to be that substance, whatever it is in that mixture, it's the substance that's the largest quantity. Everything else is a solute. So you'll always have only one solvent in a solution, but you could have one or more solutes. Now solutions, just because it's a heterogeneous mixture, doesn't mean it has to be a liquid solution. Most of you probably think about solutions as being liquids, and most of the solutions we encounter tend to be liquids. For example, there's one that we use a lot already as an example in lecture and also maybe not so much yet in lab, but you might be seeing this soon enough. That's going to be vinegar. Vinegar is a solution, right? It's not, you won't find vinegar on the periodic table. Anyone know what vinegar is a solution of? It's about 5% acetic acid in water. This is what we call a percent solution. This is 5% volume per volume of acetic acid in water. But there's other kinds of solutions. It doesn't have to be liquid. We can have solutions that are solid. For example, steel. We all know what steel is, but you won't find steel as an element on the periodic table because it's not an element. Steel is a homogeneous solution. Anyone know what steel is composed of? It's iron and carbon. But there's other solid solutions like this, like brass and bronze. In brass, it's a solution of copper and zinc, and bronze is a solution of copper and tin. I mean, there's other things in there as well, but these are the major components. But in all these cases, we have a solvent and solutes. In steel, right, the solvent is iron. In brass and bronze, the solvent is copper. But you don't tend to think of solvents as being something that's a solid, okay? But by definition, we could classify these things as solvents and solutes. Collectively, when we have when we have a solid homogeneous mixture, these are called alloys. You can also have a homogeneous mixture of gases. It's not just liquids that are mixtures. There's a very famous gas mixture, which I'm sure you're all familiar with. What's it called? It's called air. The atmosphere, right? Air is a mixture. Who knows what the solvent in air is? Go ahead. Say louder. It's nitrogen. Nitrogen is the solvent. Molecular nitrogen, okay? It's about 78% nitrogen. Of course, you think about oxygen as being in air. We need the oxygen. That's only about 21% of the composition of air. And then argon makes up most of the rest of it. That's about 1%. Now, of course, there's other things that are much less than 1% in the air that you've also heard about, especially in the context of having too much of it, like carbon dioxide or other pollutants, carbon monoxide, other nasty things in here. These are much less than 1%, but they're still very important for good reasons and bad. But the major solutes are oxygen and argon, right? And nitrogen is the solvent. So there you go. We also have solutions that are solids dissolved in liquids. See, these are all liquid and liquid, solid and solid, gas and gas. We also have solids dissolved in liquids. Like your favorite carbonated beverage, sodas. Or my least favorite drink. What's my least favorite drink? Coffee? Did you say coffee? No way. I couldn't live without coffee. No, sweet tea. I despise sweet tea. You guys don't know that I hate sweet tea? Oh, it's the most wretched thing on the planet. But it's a great example for solutions. So I'm actually going to talk about sweet tea plenty of times in lecture. So I don't like it to drink it, but I like to use it as an example. Anyway, these are examples of other types of solutions where we have, these are now different phases of matter dissolved in each other. We're also going to be talking about the concentration, how we can keep track of how many molecules we have in our reaction. We just got done talking a lot about the stoichiometry, balancing equations, and keeping track of how many moles of each substance are in the reaction so we can like make predictions and do theoretical yields and balance equations. Well, when we do that in solutions, that's much more challenging to keep track of what your molecules are because they're dissolved in some larger amount of solvent. So we're going to be talking about different ways that we keep track of the concentration. And mostly we're going to be using molarity in our class. Now, molarity is something that you've already seen a lot in the laboratory, but you haven't yet learned what molarity is. That's the capital M. That's going to be moles of solute per liter of solution. Okay, so we'll be doing some other things with that later on. All right, so let's have a little discussion then about what happens when you actually do have materials in solution. What's really going on in aqueous solution? And I'm going to use an example of this is putting sodium chloride, salt, in water. Now we all know what happens when you put salt in water. What happens to the salt? It dissociates. Now that's what the chemist would say. It dissociates. It dissociates into what? It dissociates into its component ions in this case, because it's an ionic compound. But to the non-chemist, you might think that, you know, we're magicians and you put sodium chloride in water and poof, it disappears. But it's not disappearing, okay? It's dissolving in solution, all right? Not disappearing. It's dissolving in solution. Now, that's not just for ionic compounds. Anything that disappears in the solution is actually dissolving in the solution. When you're an ionic compound, what happens is that when it dissolves in solution, what's happening is that it dissociates further into its component ions. So when it dissolves, it dissociates into its component ions. In this case, the sodium ion and the chloride ion. So notice the subscripts that I'm using for the states of matter. We take solid sodium chloride, and I'm putting it in water. So I put the water, in this case, just over the reaction arrow. And I end up with the two ions, and they're in aqueous solution. That's how we write it. But what does it actually mean? Why is it that the sodium chloride as a solid, when it's in water, why does it do this? Because we all spent this time talking about the strength of the ionic bond. right? You've got a positive charge on the sodium ion and you have a negative charge on the chloride ion. Those want to be attracted to each other. That's what the ionic bond is. So why does it fall apart in water? What's going on? Well, you may recall that water is a polar molecule. It has an overall net dipole moment over the entire molecule. Remember, we did this with the geometries. The geometry is bent. So we do have little dipoles on, they're not so little, but we have dipole moments on the two bonds, the hydrogen-oxygen bond, but it's bent, so they're not canceling each other out. So overall, there is a permanent dipole moment on this entire molecule. There is a delta negative side of water and there's a delta positive side of water. So when you have sodium chloride in solution, what actually happens here is here's the sodium ion, okay? And we've got these water molecules basically associate around the ion and stabilize it. Again, it's the positive and negatives. Now, this is a full positive charge here. This is just a delta negative and a delta positive on the dipole of water. But you have a lot of water around here. Water is the solvent. It's the most, not the most abundant. It's the material in the solution that's of the greatest abundance. So let me just draw a few of these. There's about 6 water molecules. I'll just draw 3 of them. The absolute number doesn't really matter here. That surround the sodium ion here. And notice that I'm drawing these specifically so that the dipole moments align here. I'll draw the other 2, but I just won't draw the H2O. It's aligned so that the delta negatives on the dipole moments of the water are all in contact with the full positive charge on the sodium. Now, there's also chloride ions in solution as well. So here's the delta positive side of the dipole of water. Well, that's going to be associated then with where the chloride ions are in aqueous solution. Okay. So yeah, there's an overall attraction for sodium and chloride ions together when there's just a solid. But when you put it in water, it's actually more stabilizing overall for them to dissociate and be stabilized more by this interaction with the water molecules. So it's more stabilizing than the otherwise attraction for the sodium and chloride ions to themselves. In an ionic bond. Okay. Now, this isn't true for all ionic compounds. Some ionic compounds you put in water and they stay as a solid. Other ionic compounds are like NaCl. You put them in water and they will dissociate into their component ions. That's the difference between being soluble in water and being insoluble in water. Okay, so not all ionic compounds are soluble in water. If it's not soluble in water, that's what we call insoluble. And if you're insoluble, that means that it forms a precipitant. And we would write that as an S. A precipitant is a solid. Now, these are terms that you've already heard in lab. And you've seen this happen in lab. You've done lots of reactions where you take 2 clear solutions and you mix them together, and now the solution turns opaque. Or sometimes you see a solid come from nothing, like in the copper cycle, where you had a nice clear solution, and then you did something, and all of a sudden, this solid formed. Magic in front of your eyes. Okay, it's not magic. In that case, you've changed the chemistry, and now the interaction of the ionic bond is stronger than the stabilizing force of having the ions solvated by the water molecules. Okay, here in this case, the ion is solvated by the water molecules. Okay, so we can change the conditions and have something that was soluble now becomes insoluble. Or sometimes that will happen when we're mixing things together and we're doing a chemical reaction. And when the reactants are separated from each other, they are soluble, but when you mix them together, right, we're swapping cations and anions, and now all of a sudden they become insoluble in water. Okay, so, and it's not all or none. It's dependent on a lot of things, and I'll touch upon that in a little bit. But first, I want to orient you with this table from your textbook, the solubility guidelines. This is a table, it's just guidelines. These are not rules, okay? These are guidelines, not rules, okay? But these are general guidelines for when you will find common ionic compounds that are soluble in water, and this is under standard laboratory conditions. Meaning that the pressure is about 1 atmosphere, temperature is a nice comfortable 20 degrees Celsius or 25 degrees Celsius. All right, it's not too bad. What you would normally encounter if you go up to the Gen Chem labs and you look at these materials, you will generally find that they will be soluble in water under these conditions. So for example, if you look at section 1, all of these compounds containing the following ions are soluble. If you look at condition 2, all of these are going to be soluble. And if you look at section 3, and this is one place where students sometimes get confused when they look at this table, section 3, these have limited solubility. So you can think of these as being insoluble. But it's not completely insoluble. Okay, it's limited solubility. So we just did sodium and chloride. So let's take a look at rule 1. All compounds containing the following ions are soluble. Again, in general, under normal laboratory conditions, standard laboratory conditions. Any cation that's from the group 1. So that's the alkali metals. So everything, so sodium, lithium, potassium, rubidium, cesium, all right? Group 1 metals. If that's the cation, it's going to be soluble. And we also have the ammonium ion, polyatomic ion, NH4+. Okay? If you're looking at the anion in the ionic compound, all right, that also we're going to add the polyatomic ions, the nitrate ion, right, and these others. If you look at an ionic compound and it has these materials, it will always be soluble under standard laboratory conditions. If you look at section 2, here's the chloride ion. So sodium is up here. Sodium is a group 1 metal. So if it contains sodium, then it doesn't matter what the anion is. If it contains sodium, it will be soluble in water. Now, looking at the anion though, right, compounds that contain the following anions are soluble, but there are some exceptions. So here's chloride ion. And sodium, of course, comes in with chloride. So sodium chloride is going to be soluble. But the exceptions for chloride ions are when they're partnered with the cations for silver, copper, mercury, or lead. Those are exceptions. Right, so we're going to come back and look at one of those exceptions in a minute. In particular, when it's paired with the silver ion. And you've done this experiment already. When you make silver chloride in the lab, that's going to precipitate as a solid in the solution. That was that milky white opaque solid that you formed in some of the reactions that you've done. You remember that? Hopefully you remember doing that, and you'll be doing it again. All right, there's more that I could talk about on this table, but I'm going to probably refer back to this table several times over the next several lectures. All right, right now I just want to start orienting you about what information is in this table and how to extract that information from this table. Now, going back to this example up here, when things are solvated, I told you, sometimes they're soluble, sometimes they're insoluble. Now you know how to read that from the table. But why is it that some materials are going to be soluble like this, whereas others won't be? All right. It's always going to be sort of a trade-off between this kind of stabilization versus this stabilization. For sodium chloride, it turns out that it's more stable when it's solvated by water, but that's not always going to be the case. And there's lots of things that factor into that. But one of them comes from this down here, which I probably have I lectured to you about this equation before when we saw this back in. This is Coulomb's law. And we can look at this relationship very briefly, just to kind of get an idea of what's going on here and to help you understand what's happening in the table. Q1 and Q2, these are the charges. This is the cation. This is the anion. These are the charges. So for example, with sodium and chloride, it's a 1 plus and a 1 minus. But if we had magnesium chloride, that would be a 2 plus and 1 minus. And then this is D. This actually should be D squared, distance squared. This is the distance between the two ions. And this is simply the electrostatic potential energy. So this is your attraction. This is what we're competing with versus that stabilization with water. Okay. The stronger the charges are, all right. So when you have a +2 or a 2 minus or a 3 minus or a 3 plus cation and anion, that's going to give you stronger charges between the ions. That's going to increase the value of the numerator. So that's going to increase the electrostatic potential energy, give you a stronger ionic bond. However, as the ions get larger, as you move down the periodic table, or as you start building polyatomic ions, those things are much larger. So the distance between those positive and negative charges is getting farther and farther apart. So the larger the ions are, the greater the distance between them. And so now you're decreasing the electrostatic potential energy. So it should be more favorable to be solvated in water. So as an example, if we look at, here, let's look at this one, hydroxides. Hydroxides tend to be limited solubility, except for those of group 1 cations. And look at this, calcium ions, strontium cations, and barium cations. What do we have above calcium in the periodic table? Magnesium. Okay. So when we have magnesium oxide, that's only partially soluble. Anyone ever take milk of magnesia? It sounds horrible, doesn't it? Milk of magnesia, right? That's what this is. That's magnesium hydroxide in aqueous solution. It has limited solubility, so it gives you this like thick, milky stuff. This has limited solubility, but as you get larger in the ionic radius here, the calcium ions, the strontium ions, those are much larger, even though the magnitude of the charge is the same. The distance between those cations and the hydroxide polyatomic anion gets larger and larger. All right, so this is going to influence the denominator. So as the ion gets larger, the solubility increases because now the electrostatic potential energy is lower in the ion, in the ionic compound. So it's going to be the stability of being solvated by water is going to win that battle. There's other things that factor into solubility, like temperature and pressure and concentration. I'll talk about some of those things in a little bit. Right? But this is also one thing that helps you at least understand why it is that some things are soluble where other things are not. All right, so we'll come back to this table as it's relevant. But now I want to show you an example of some of the things that you're going to be doing in lab. We're taking this into the lab now. We're going to be talking about precipitation reactions. Right? That's what happens when you take two things that are soluble, mix them together, and now some solid precipitates out of that because now it's become insoluble. All right. Here's a reaction that we balanced last chapter. Silver nitrate mixed with iron 3 chloride gives us iron 3 nitrate and silver chloride. I think we just did this one like Friday or last Wednesday. So I'll just jump to the end, right, for the balancing act. Well, let's just practice balancing real quick. We have, remember, you keep your polyatomic ions as polyatomic ions. So we have 3 nitrates over here and only 1 nitrate over here. So I can balance the nitrates with the coefficient 3. That gives me 3 silver cations on the left. So it will give us 3 on the right. In doing that, it now gives us 3 chlorides on the right. And we look on the left and we have 3 chlorides. There's 1 iron, there's 1 iron. So now we're balanced. Okay, that one's fairly straightforward. Now you've also been learning in lab about different classifications of reactions, like single replacement reactions and double replacement and combination. So what kind of classification of reaction is this? It's a double replacement reaction. Most, but not all, double replacement reactions can be often found as precipitation reactions, and they're where you have ionic compounds and they're swapping their cation and anion partners. So we write this as one ionic compound, AB, and remember we always write cation first and anion second. So AB in aqueous solution is mixing with CD in aqueous solution. And now we swap our cation anion pairs. So that's going to give us AD plus C as the cation and B as the other anion. Now I haven't put the states of matter on here yet, because what you're going to do in a double replacement reaction is you're going to take a look at the reactants. You're going to do your double replacement. Of course, you have to make sure that the stoichiometry of the atom types within each cation anion pair are the same, or give you a net neutral ionic compound. Remember that. Okay, so you swap the partners, then you have to make sure the subscripts are right. And then you can go and look at the solubility guidelines and take a look. Well, should this be soluble or should it be insoluble? Especially if you do this mixture and you find that one of them is solid. If something precipitates, that means one of these is going to be in aqueous solution and the other one probably formed a solid. And you can go and consult the solubility guidelines to tell you which one of those two, was it AD or CB, which one formed the solid. So here you go. We've got aqueous solution here, aqueous solution there, and we mix them together. And the molecular reaction tells us that we have iron 3 nitrate in aqueous solution and silver chloride solid. Now, if you were doing this and didn't know this reaction, all you would do is mix these two clear solutions. This one is clear. This one is clear. And this product here, this new solution, when you make the mixture, this has a white precipitant. Right? That's what you did in lab. So you would see, okay, this made a precipitant. One of my products is iron 3 nitrate. The other one is silver chloride. Go to your solubility guidelines and figure out, well, in section 1, it's telling me that if I have the nitrate anion, it should be soluble. So it won't be the silver 3, it won't be the iron 3 nitrate, because solubility guidelines tell me that nitrates, compounds with nitrates are soluble. And I take a look, the other prediction is for silver chloride. And so I look for chloride here. And I see this exception: when silver is with chloride, it's solid. So that must be what the solid is. All right, that's the logic of this. But now let's take a look at what's really happening in this solution, because it's not really like the way it's drawn or the way it's used in our shorthand. This is the molecular equation. It's a shorthand. Just like with anything, with any model that we use in chemistry, we have symbols, we have models. You have to know what they mean. The molecular equation that we've been using all along, it's just a shorthand. What is it really telling us? What hand is it shortening? Let's take a closer look, because we just had this nice discussion about when sodium chloride is in aqueous solution, what's really happening in solution. It's being solvated by the water molecules. So if it's listed as aqueous solution, this means it's solvated by the water. Okay, so let's actually show what's happening in solution here. If in the balanced equation, we have 3 silver nitrates in aqueous solution. So what that really means is we have silver plus ions in aqueous solution. Actually, we have 3 of them because we had 3 silver nitrates. And just like I showed you for sodium chloride, it dissociates into its ions. So this dissociates into 3 nitrate ions in aqueous solution. That's really what's happening from our shorthand. I'm just showing you what's actually happening in solution. What I'm writing out for you here is what we call the full ionic equation. It's what's really happening in solution. All right, so let's continue along. Here we have 1 iron 3 chloride, but it's listed in aqueous solution. So we're now going to take our shorthand into the full ionic equation. In aqueous solution, what we really have is iron 3 plus ions in aqueous solution, plus, now look at this. Each mole of iron 3 chloride has 1 mole of iron 3 plus cations and 3 moles of chloride ions. Do you all see that? The subscript 3, it tells you that it's a 3-to-1 ratio. So when this dissociates in aqueous solution, this is going to dissociate into 3 chloride ions in aqueous solution. You all see that? Okay, and now on the product side, we have iron 3 nitrate listed in aqueous solution. So I'm going to go ahead and split that one up. That's, again, iron 3 plus in aqueous solution. And now I have the nitrate ions here, but once again, we have a subscript 3. So when this dissociates, when it magically disappears in solution, it dissociates into 1 part iron 3 plus cation and 3 parts nitrate ions in aqueous solution. Now, here's a common mistake that students make, so don't be that student. In our molecular reaction, it says that silver chloride is solid. That means that in aqueous solution, it stays as a solid. So if we're writing what's actually happening in aqueous solution, this stays as a solid. We don't break that apart. We're only splitting apart things that our shorthand is telling us are really ions that are solvated in the water, just like I showed you for the sodium and the chloride ions. Okay, so basically, if it's a solid, it stays a solid. If it's a liquid, it stays a liquid. If it's a gas, it stays as a gas. The only thing that we're really breaking apart into its components, I know I've said this 3 times now, it's that important, right? I see students mess this up all the time. The only thing that we're breaking apart here are the things that are listed as being in aqueous solution, the ionic compounds in aqueous solution. All right, so now let's take a closer look at our full ionic equation. And I've got some bins here, so I'm actually going to draw this out for you. If we take a look at the silver nitrate here. When we have the silver nitrate, here's our starting, all right? Silver nitrate and iron 3 chloride. We're going to mix these together. This is what you're actually doing in the laboratory. So these, as I mentioned, but then I erased it, these start as clear solutions. So let's draw what's actually here. What's swimming around in these clear solutions? We have silver ions in aqueous solution, and we have nitrate ions in aqueous solution. They are more stabilized, being solvated by the water molecule. So all we see is a clear solution. The same is true for the iron 3 chloride. We've got iron 3 plus here, and just to show this in their correct ratios, all right, I'll do it this way. But when we mix them together, now we get something else. And I can tell that, more thoroughly what's happening here in the full ionic equation. I have some things that remain as ions in solution, and then I have this new cation-anion partnering of the silver and the chloride, which is now a solid. So that solid's going to be down here. This is the silver chloride solid. But still, we have swimming around in solution. We still have the iron 3 plus ions, and now we have 3 nitrate ions. All right, so I didn't write this out so it's completely balanced, but I think you get the idea. So once again, what's really happening here? I know this looks even more complex than what we had up on the top. But if we take a closer look at the full ionic equation, we can actually simplify this greatly. Because notice that on the reactant side, we have 3 nitrate ions that start the reaction. This is the actual reactant here. There's 3 nitrate ions in aqueous solution. And look on the product side. We have 3 nitrate ions in aqueous solution. The reaction started with them there, and the reaction ended with them there. And as you look at the drawings here, hopefully you'll realize that the nitrate ions aren't doing anything at all. They're not reacting. They're simply there to bring the cations and anions together that are reacting, the silver and the chloride. You can't go to the laboratory and find a bottle of silver cations lying around. They're always partnered with some other anion in this case, right? So in this case, we're bringing it in as silver nitrate. But in aqueous solution, the nitrate ion isn't doing anything. It starts in solution and it ends in solution. So just like in a mathematical equation, we can just ignore them. They cancel out. It's the exact same thing. That's why I'm canceling them out. There's nitrates and there's 3 of them on each side, so they completely cancel out. What else cancels out in this way? The iron 3 plus. We start with 1 mole of iron 3 plus in aqueous solution, and we end with iron 3 plus in aqueous solution. So we can ignore them. In fact, they're not involved. These are what we call spectator ions. Spectator ions are not involved in the reaction. They're just hanging back, kicking back in their lounge chairs with some lemonade or margarita, if you prefer, watching the reaction happening in front of them, but they're not involved at all. So what is the reaction? Oh, hey, look at that. I forgot to bring down a 3. Oops. Notice when I did the full ionic, there's 3 silver chlorides here. I need a 3 here. Any balancing that you do, you got to bring that down into the full ionic. All right, so now let's take a look. What is happening then is everything that's left over once we remove the spectator ions. That's going to be, we have 3 moles of silver cations in aqueous solution, and we have 3 moles of chloride ion in aqueous solution, and they are going to combine to form 3 moles of silver chloride solid. And because it's 3 to 3 to 3, we can reduce these coefficients down to 1 to 1 to 1, right? We want to do that with our balancing. We always want to reduce this to the lowest whole number ratio. So that's going to reduce down to 1 mole of silver ions in aqueous solution plus 1 mole of chloride ions in aqueous solution will combine to give us 1 mole of silver chloride. That's solid. This is the only thing that's happening in this whole complex reaction here. This is what we call the net ionic equation. This is the actual chemistry that's taking place. Now, the net ionic equation does look a lot more simple than compare that with the molecular equation, the shorthand up on top. That shorthand makes it seem as though partners are swapping and they're doing a little dance. And then, we end up somehow getting a solid form there. But really, the only thing that's happening is the net ionic equation. So that's what we're going to be focusing on in your lab exercise this week. All right, we'll finish up with a couple more terms here. So we've been talking about solubility. And I mentioned to you briefly that there are lots of things that impact the solubility. We did talk about Coulomb's law. That's one thing. Okay, so let me add this here. But also the volume has an influence on it. I mean, at some point, here, let me show you this example. Let me give you some slide whiplash. Go back here. At some point, if we keep adding sodium chloride to this solution, what's going to happen? Is it all going to stay dissolved? No. What happens when you make sweet tea and you add sugar to the solution? It dissolves until at some point you add too much sugar, and what happens? It just sits at the bottom. It no longer dissolves. So there's some point at which effectively you run out of water molecules to do this. Okay? If we keep adding sodium chloride to this water, at some point when we run out of enough water molecules to solvate everything, now it's going to go back to the attraction it started with, the ionic bond, and it will stay as a solid in solution. When that happens, we say that the solution has become saturated. Okay? So saturated solution, that's the maximum amount of solid that we can dissolve in that volume, given the pressure and given the temperature. Okay, those are other things. I didn't talk about those. Oh, here, ionic charges and distance between nuclei. That's the Coulomb's law. I should have seen that here. Okay, so if you increase the volume, then let's say you put too much sugar in your sweet tea. Well, if you add more water to that sweet tea, you'll probably get it to go back into solution. So the volume has some effect on whether something is soluble or not. The temperature has an effect. When you make sweet tea, you think I'd like it. I talk about it so much. When you make sweet tea, do you add the sugar to cold tea or do you add it to hot tea? Why? Why do you add it to hot tea? Because it dissolves better, right? Solubility is also temperature dependent. Okay? Solids tend to have higher solubility at higher temperatures. Okay? The pressure is going to have an effect as well. I don't need to talk about all these things. Right? And I'm not going to be testing you on all those individual ones as well. Well, maybe a little bit. I don't know. Right now, let's just stay focused on these general ideas, right? Volume, that certainly has an effect. Temperature, that certainly has an effect. Well, sure, let's talk about all of them. I mean, the pressure. Now, you know what? I only have a few minutes left. I want to get through the rest of this. Let's stay focused on volume and temperature for sure, and also the ionic changes. Those three I'd like you to be familiar with. Okay, so that's why I have check marks there. Okay, so that's what happens when it's saturated. When it's unsaturated, that means the solution is still clear. There's no precipitants. That just means that we have a sub-maximum amount of solid dissolved in that particular volume at that particular temperature and pressure. So those terms should be fairly straightforward to you. When you're right at that magic point where you can't add any more solids and have it remain soluble, that's what we would call the saturation point. All right. The saturation point is basically that threshold. Yeah. You can all write that down in your notes if you want. All right. I'm going to write down border. I think you know what I mean by that. If you read this in the textbook, they show you an example of a special case that we call supersaturated. This happens when you have something that's warm and you cool it slowly. So when it's warm, it can it can dissolve more of the solid when it's at a higher temperature. So when you then slowly cool that temperature, now theoretically, you've created a saturated solution, but you do it coolly enough that it still looks clear. Here, let's just say when we slowly cool, we've crossed the saturation point line. So we cross the saturation point, but it stays clear until you do something to add a little bit more energy to the system. In this case, in the picture from the textbook, it's seeding the reaction. You seed it with a few crystals. And just by giving the supersaturated solution a few crystals of that ionic compound, it now seeds the precipitation, and all of a sudden, like, whoosh, everything comes out of solution very, very quickly. You can also achieve the same thing by just taking your stir rod and scraping the bottom of the beaker. It gets the same thing. This is just a special case. I'll just put this in parentheses for you. I really want you to stay focused on saturated and unsaturated solutions. When it is saturated, here's your sweet tea. You're going to have some undissolved sugar sitting at the bottom, and you're still going to have sugar that's solvated. But that won't happen, of course, until the solution is oversaturated. So the way I've drawn this is we've got some sugar that's swimming around in solution. All right, I'm going to say this sugar is an aqueous solution. So I'm going to put a little AQ sign here. Whereas this sugar that's undissolved, that's in the solid. Now you walk away and you come back in an hour and there's still undissolved sugar there. In fact, if you were to take a careful measurement of it, you'd probably find that there's the same amount of undissolved sugar there. And you come back an hour later and there's still the same amount of undissolved sugar there. So it looks like it's not changing. When you have an oversaturated solution that's at this equilibrium, it looks unchanging, which is what we call static. Static means you're not changing, you're not moving. But really, what's happening here is you have what's called a dynamic equilibrium. And when you have a dynamic equilibrium, what's happening is some of the undissolved, some of the solid sugar is redissolving and going back in aqueous solution. But the reason it doesn't change is because that's balanced by the same amount of sugar in the aqueous phase, reprecipitating and going back into the solid. So it's constantly going back and forth. And we would write it this way: whatever's in aqueous solution is in equilibrium with whatever's in solid. And we have not a reaction arrow that goes in one direction, but we have a reaction arrow that goes back and forth. It's in equilibrium. Now, this is something for those of you who will continue on to Gen Chem 2, we'll be exploring equilibrium in a much greater detail. There's a lot more involved here than just saying that the concentrations look the same, but they're just the amount that goes into solution is countered by the amount that goes back in. So I'm not going to talk about it anymore. If you take me for Gen Chem 2, we'll have a longer conversation about it. But it is important to know that when you have an oversaturated solution, what's really happening here is this dynamic equilibrium.